All right, welcome back, everybody. This is section 1-2, mathematical models. Mathematical models. So in the last section, we talked about why we need functions and why functions are useful within math. And we talked about how it relates to real life and saying, okay, if we see a pattern in our world, we can try to model an equation after it, thus creating the necessity for functions. We're still on that track, but now we say, okay, how do we create those functions? That's what we're really looking at today. If we see a pattern, if we see something happening, how do we create those functions? A mathematical model is a mathematical description, often by means of function or an equation, of a real-world phenomena such as size of population, demand for a product, speed of falling object, concentration of a chemical, or a concentration of a product in a chemical, whatever it may be. It could be anything. A mathematical model is just something that models a situation, an equation that models a situation, right? Like back in Algebra 2, we learned about linear models and quadratic models and cubic models and logarithmic models and exponential models. And we did all of those, regressions in our calculators to model certain situations. That's really kind of what we're going to review today, right? So again, this is kind of like the process that you should take. You find a problem, you find something that's going on in the world, and then you say, okay, how can I create an equation to model this situation? How can I create an equation to predict something that's going to happen in the future?
Attention, please. Sophomore, last name starting with I through P. Please go to the performing arts hall to have your photo taken. Then sophomores, last name starting with I through P. Go to the pod now. Thank you.
You're welcome. So we create a mathematical model, we create an equation, and we see, okay, we believe that this is going to predict what's going to happen in the future. Companies will pay big bucks if you say that you can predict the future, right? So man, to be like a mathematician, to be like a statistician or something like that, man. Okay, then you solve that problem. Then you say, okay, I am going to solve that problem. I'm gonna crunch the numbers. I'm gonna do the math. You make your conclusions about that. You make your inferences. Then you interpret your results. Never be and then make predictions. But never be naive to think that you're not going to have to start back over again. Never, we all make mistakes. We all have some variables that we never think about, and that causes something to happen that we never expected. So maybe we have to go back and rework our models and whatever. Okay. All right. So let's start with our most basic type of model, the linear model. The linear model. When we say that y is a linear function of x, we mean that the graph of the function is a line, obviously. So we can use the slope-intercept form of the equation of a line to write the function. Yeah, I mean, back in Algebra 1, we learned slope-intercept form, y equals mx plus b, where m is the slope and b is the y-intercept. It would be great to say that everything falls exactly on a line if it's a linear function, right? We can say if it truly is a linear function, it is exactly going to fall on that line. Now, life's not always that nice. We'll talk about that in a second. But take, for example, this one. As dry air moves upward, it expands and cools. If the ground temperature is 20 degrees Celsius and the temperature at height of 1 kilometer is 10 degrees Celsius, express the temperature T as a function of height, assuming that a linear model is appropriate. And what am I going to use here? I'm going to use y equals mx plus b. F of x is equal to mx plus b. Or in this case, t of h is equal to mx plus b. Now, what they give us here are two coordinates. And can you make a line out of two coordinates? Heck yeah, we can. So let's create our two coordinates here. We know that at ground level, at 0 height, we have 20 degrees Celsius, right? And our input is height. Our x value in this case is height. So we've got 0, 20 degrees. We also have, at a height of 1 kilometer, the temperature to be 10 degrees. So it's cooling as we go up, right? As I increase my x value, my y values are decreasing. negative slope, probably, I guess I should say. All right, so let's find the slope. We've got y minus y, x minus x. 20 minus 10 is 10 over negative 1, negative 10. So we've got negative 10x as my slope, negative 10. And then what's my y-intercept here? They give it to us, 0, comma 20. Perfect. That's nice. Our starting value. Okay, there's my function. Negative 10x plus 20. Oh, I shouldn't say x. Excuse me. Excuse me. H. Right? If you define a variable in your function notation, use that variable. Bad form to just make an x. All right, so let's draw the graph of the function and identify what the slope represents. Oh man, I still haven't gotten myself a good graph. Oh, that's okay. Did we talk about domain yet? No, we didn't talk about domain yet. All right, let's graph it then. I want to have a y-intercept of 20 and a slope of negative 10. And actually, I do this. Now, why am I doing this? Because can my x values, or actually can my y values turn negative? Can my outputs be negative in this case? Can temperature go negative? Yeah, temperature can go negative. So that's why I actually run myself into the bottom there. I was only going to make like our standard word problem X, Y, quadrant 1 chart, but I got to drop it down because it's going to be negative at some point. Okay, so let's go. We got 5, 10, 15, 20. There's my top end. 5, 10, 15, 20, bottom end. And let's go height of 1 kilometer, 2 kilometer, 3 kilometer, 4 kilometer. All right, so we'll just put a scale on that. That's 10. Oh, no. I made it in 5s, didn't I? Whenever you label a graph, you only need to label 1 because I assume the interval is going to continue. All right. Now, can my x values be negative? I'm going to say we're not going to study underground, right? I'm going to say we're going to stop at ground level. So that's why I don't go to the left. So 0, comma 20. And then we have 1, comma 10. And I can continue this pattern if I really wanted to, right? I only need 2 points to make a line. So I can generalize it to that. But if I wanted to run another number, all right, what's 2? Oh, I made this really off then. Because what should 2 turn out to be? Oops. Let's go back then. Okay. This is why I need a better graph. Oh, geez, I made that worse. There we go. There we go. Much better. All right, so there's the graph of this function. And what does this slope represent? We are going to study slope so much this year. Like, slope is one of the biggest topics of calculus. I know that seems weird to think, like we're going back to slope, really? Like algebra 1 slope, like what, rise over run? Yes, we will study slope a lot. So what does the slope actually represent in this case? Well, it describes the rate of change, right? Change of what? Temperature as I as I increase height, right? It's change in temperature as I increase height. The temperature is decreasing as my height is increasing. It's the rate of change. Rate of change is a very important phrase that we will use a lot. And then we could say, what is the height at a temperature, what is the temperature at a height of 2.5? We could guesstimate it using the graph, but why would we? We have a function. Let's find T of 2.5. So we have negative 10 times 2.5 plus 20. I didn't really need to put that in -5. You know, thinking back to my timeline of studying, making predictions, and then having to go back at the very end. Think about it this way. I said my domain was like, just h is greater than 0. Would this pattern still continue forever? Like, do you think it would just keep getting colder and colder and colder and colder and colder as far as I go out into space? Now, at some point, the temperature probably levels off, right? And I don't know what it looks like later on. I just know in this specific snapshot of time that it looks linear and that we can model it using a linear equation. Right? So, you always have to think about, okay, what could happen in the end? Is this a good model for what we've got right now? All right. If there's no physical law or principle to help us formulate that model, like in this case, we had data and we could say that this was definitely going to fit a linear model. If there's no physical law or principle to help us formulate that model, what we could do is construct an empirical model, which is based entirely on collected data. What that means is basically we're going to run a regression, right? We're going to find either a linear regression or a quadratic regression, and we're going to use technology to help us along with that. We're going to use our calculators to help us along with that. We seek a curve that fits the data in the sense that it captures the basic trend of the data points. So if you see create an empirical model, that term empirical model just basically means throw it in the calculator and see which one is the best fit. Right? See if a linear model fits or a quadratic model fits or a cubic model, whatever it may be, see what model best fits the data. Okay? And again, we're looking for empirical model. That's what tells you in that case. Okay, I'm not going to make you create a scatter plot. Like that's back in Algebra 1. I make my Algebra 1 students create a scatter plot. I think at this point you're good with getting scatter plots. Take a look here though. I want to show you an example that the book says you should do on your own, but in my case, I'm not going to make you do that. Table 1 lists an average carbon dioxide level in the atmosphere measured in parts per million at Mauna Loa Observatory from 1980 to 2012. So we're looking at carbon dioxide level, and that's Hawaii, right? I think that's Hawaii, Mauna Loa. From 1980 to 2012. Use the data in table 1 to find a model for the carbon dioxide level. Okay, so what are we looking at here? We're looking at carbon dioxide level looks like it's spaced out every 2 years. They make an observation every 2 years from 1980 to 2012. And we can see the trend in the data is going upward. It looks linear, right? It looks linear in this specific snapshot right here. Is it exactly linear? Like if I choose my line tool and I start on the front one and I go to the very end one, there is a little variation, isn't there? Right? It's not exactly linear, but it's quite close to being linear, right? We're going to say that this probably is a very good fit. That linear model is probably a very good fit for that. Now, if you choose to take further classes in college on maybe in statistics or whatever it may be, there are ways to create a linear regression by hand, like actually create using and figure out, okay, what would the best slope be and all that sort of stuff. Okay, what we're going to do is we're going to use our calculators to do that. Okay, we're going to actually use our calculators to do that. So go ahead and get out your calculators. Okay. If you don't have it, just follow along. This will probably ring a bell. Right? This is probably going to be like, oh yeah, that's how we did it way back when. I'm going to move this guy over just a hair so I can see my full calculator. Okay. You didn't? No. Oh. You need one. Yeah, I ordered one. It's coming tomorrow. That's a good idea. Okay. All right. So remember, you go to Stat, and then you hit Edit. I got nothing in my list. I haven't done this in a while then. And then you're going to input all your data. Okay. I'm gonna zoom in on this table so you guys can see it a little bit better. I would try to do this along with me just in case you have any issues or anything. There's the data. I'm going to plug mine in using my keypad here. There we go. What time does this bell ring?
17.
Oh, good. I thought it was 13. And I was like, oh, shoot. That's not going to work. Okay, looks like we should have 17 pieces of data. 1, 2, 3, 4, 5, 6. 17 pieces of data. Put the years in list 1, and then I'm going to put the CO2 level in list 2. Always make sure your lists match up, right? You never want to skip a entry or anything like that. That'd be bad news. And just kind of spot check. Just say like, okay, look at 2002. Is it 2002, 373.3 or 373.2? Yeah, okay, good. Just kind of spot check a couple ones, make sure they're still correct. All right, so remember, once you get your data entered, you go back out to your home screen, and you're going to go Stat, Calc, and then here are all of your regressions. You see linear, quadratic, cubic, quartic, and you could keep going down there if you really wanted to. There's a linear regression of a plus bx. There's a natural log regression, exponential regression, power regression. There's a logistic regression, which we'll actually talk about this year, sine regression, all that junk. All right. Let's do linear regression, ax plus b. Okay, it's not giving me my R value. Remember R value? R value is the strength of your correlation, right? Like we looked at the scatter plot and we were like, wow, that's really linear. But how do we represent that mathematically? By an R value, by a variance. Okay, so to get that R value, you have to turn on your diagnostics. So to do that, you just hit second catalog. That's the best way to find it. And just either hit D or scroll down to D and turn on your diagnostic. And you have to hit done, and then you just rerun your regression. Stat calc 4 is linear, ax plus b. It's giving us an r squared value as well. Really, we're looking at the r value. The r squared value is just like a even stronger value because you're squaring your variances, making your variance even bigger. All right, so we got y equals mx plus b here, ax plus b. So this is y is equal to, oops, I guess I need a pen. Y is equal to 1.7126 x minus 3054.1417 if I'm rounding to 4 decimal places. And I'm getting super exact with even 4 decimal places out, right? That is my mathematical model. That is my equation. I better check my answers. 1.7126x. Yep. That is my equation that I can use to model this
Your
situation.
attention, please. At this time, sophomores, last names starting with Q through Z.
Q.
Please report to the pod now to have your photo taken. Then sophomores, last names starting with Q through Z. Please go to the Performing Arts Hall now. Thank you.
So we've got, here's my equation. And again, what I can say here is that no matter what x value I pick, I can now make predictions on the future. So, the book says, use the linear model given by equation 2 to estimate the average CO2 level for 1987. Okay, what am I doing here? I'm actually looking back within my data and saying, okay, what would have been, using this model, using this trend, what would have been in 1987? So I'm just going to go back in. Because this is linear, I can just say 1.7126 times 1987. Oh, no, I wanted parentheses. Wanted a parentheses right here. Okay. 1987 minus 3054.1417. And I can say within this model, it should have been about 348.79, which makes sense. It's right in the middle there, right? Right between 1986 and 1988. I didn't have that data, but using this model, I could say, well, we believe that in 1987, it was this value. Let's figure out what it would be in 2020. Or 20, I guess it's not 2021. 2022. I had to check the year. I actually looked at the year for that. 408.7355. I wonder if this is easy data that we can look up. What are we doing here? CO2 level at Mauna Loa Observatory. Let's see if we can quickly Google this. Let's see how good this model is. CO2 level at Mauna Loa Observatory. Oh, 400. Wow, that was easy to Google. 419 parts per million. Like, I did not expect that to be so readily available. What did we say it was going to be? Oh, so our model is poor. It is not a good model. So we thought it was going to be 408. It's actually 419. Ooh. Things are getting bad. Global warming. Oh, that was in 2021. Is that what that says? Okay. Let me rerun my calculation then, because maybe that made the difference. It didn't. It actually is going to be lower, isn't it? Right. So what can we say about our model? This didn't end up being very good in the long run, right? Other extraneous factors were causing other stuff to happen. We'll continue on tomorrow when we start talking about polynomial models as well. Okay. All right.